Well, hello! So today I'd like to talk about this book, Quantum Physics, MiniBlack Holes, and the Multiverse. And this is a book from this Multiversal Journeys series. I really like the Multiversal Journeys series. So I have several of these at work. Originally, I was just going to start on the table because actually I keep these at work. I don't bring them home usually. So they're not on one of my bookshelves at home like the previous books I was showing you. So I saw that there was a new one and I picked it up and I started reading it. The first surprise about this book was the size. So you're looking at this, you can't tell the size because it's just on a little screen, right? So it could be any size. But here's Survey. Here's a standard physics textbook. Probably you've seen a standard physics textbook in your life, right? And they're huge, right? They're way too large. They are, say, the size of a piece of paper, right? So here's a piece of paper with some drawings on it that I'm setting up something else for. These are just huge. This is in comparison to one of my other books, right? So the Oxford series, still rather large, but not huge. Or a standard Springer book. A standard Springer book is about this size, right? So the previous guys in this series were the Springer book size, or the size of the standard Springer book. So when I got this and I picked it out and it was huge, well, it's large, right? It's this size, right? It's paper size, not the normal size. It's not really large, it's not thick, right? It's only about 200 pages, but it was just so large that I was a little bit surprised because the previous volumes in the series that I own were a little bit too large. I also have to apologize for the audio because right now I don't have a way to use this scanner or this, yeah, it's a book scanner actually, but this scanner and my headset at the same time, so I move away a little bit and I get far away from my screen. And I'm going to be talking at the book in a few minutes, so it's going to make it even worse. So this book was very, very large. Now the second thing is, this says debunking common misconceptions in theoretical physics. Well, this is extremely light on the math. This is basically conceptual physics level work. You see, probably seen this particular image before too for Schrodinger's cat, as well as this particular image for Schrodinger. I've in fact drawn that particular image for Schrodinger actually fairly recently. I probably should have pulled that out. It's probably very, very close right now. And so you can see it's very conceptual. It's something that you could do a 100 level class with, for example, or if you wanted, you could just read the text at least at the coffee shop, right? You can just sit there at the coffee shop, read this with quantum physics, MiniBlack Holes, and the multiverse on it. Everybody will think they're cool because you're at the coffee shop, and everybody at the coffee shop loves physics, especially weird physics. You know who else loves weird physics? These guys, Multiversal Journeys guys. So this is, I don't know if it's a corporation or a non-profit organization or something. I did pull up its website. Since I'm on a website thing now, I can show you. This is their website. So these guys, with this, and here's the book, with this website, and have a lot of educational things going on there. Oh, look, there's Sean Carroll looking scary. Misconceptions about quantum physics, all very interesting. This basically the things that we're talking about in this book. So these guys have their own, I'm not sure if it's a business doing this. They get printed by Springer, right? Really good company. We saw that just a second ago. Great books for people who are really interested in things. Good scientific press. But this is a conceptual book, even easier, even fewer equations than their previous books. I probably should look at them and see exactly what's in them before I say something like that. Now, like I said, I did like those books quite a lot. For example, we did that episode in Physics Frontiers on exact bars 2T physics with two different times, and one of the books that we have talks about that. I'm sure they also talk about the multiverse in at least one of those other ones. So, surprising two ways: it's huge or it's large. It's not huge, it's large. It's in this large format, which makes it look like something that you'd use for a class. And so maybe I will. And two, it's at that sort of conceptual physics level. We will talk about, it does have equations in it, we will talk about that in a few seconds, but I'd like to look at this first. So what we said here originally was that these things, when we look at them, we like to look at these contents. So there are three authors here, each one contributed a part. One is quantum physics, one is the MiniBlack Holes. Actually, it's a lot more stuff than MiniBlack Holes. And the last one is the multiverse. So here we have quantum physics by Bill Poirier. Poirier probably. With Bill, that sounds like an American name, so it's probably just Poirier. And he's talking about different things about quantum physics. First, he's just talking about the quantum, right, what quantum mechanics is, and he gets here to 1.5, which is how to use this. So first he's just sort of introducing things, but this 1.5 is important because, oh, look, there's declining. We have these different symbols. So these are, I think they're probably very useful for education, I'm not sure. But these different symbols mean different things. Here's some math, right? This is a misconception, this is accurate, and then this is the moral of the lesson. And this means go to the webpage. And as you saw from that webpage that I flashed at you before, they have all sorts of videos that actually relate to this particular book on it. All right, so that 1.5 is important. After that, he goes on to talking about wave-particle duality. He's talking about more or less what's going on with the early experiments, I'd say, wave-particle duality. And there was a pretty good page for this. Yogi Berra versus Yogi Berra. Probability waves. Here's a good page, right, where it shows on this page all of the things that are really important for those symbols, right? The misconception, and the misconception here says there's nothing weird about quantum mechanics. You can reconcile the wave-particle duality stuff. More accurate, it's actually really weird. Sorry. You can't get rid of the weirdness. And finally, the lesson. You can't explain away the things you don't like about quantum mechanics. And that's going to become more clear later on in the text as well, obviously, when he talks about more experiments. He's going to talk about two different kinds of experiments later on. Chapter 3 is going to be the first place where he talks about those experiments. Sorry if I talked to the book. I'm sorry. This chapter 3 is going to talk about the double slit experiment, basically. A very good way to introduce the weirdness of quantum mechanics. When I taught modern physics, I did that. I've got an hour-long lecture of, what happens in different cases with different objects and things like that. So this really describes to you, when you look at it, why quantum mechanics is strange, this double slit experiment, because it shows that depending on what you do, you either get something that looks like a wave or like a particle, and there are ways to make it look less like one and more like the other and stuff like that. Basically based on your measurement cycles. But that is very, very strange. Is this thing a particle or is it a wave? Well, we don't know. Or maybe it's both, or maybe it's neither. Somewhere in here, oh, there it is, wavicle. He's using wavicle as a thing, because it's not a wave, it's not a particle, it's a wavicle. That's not my favorite term. Just quantum particle is fine. You don't have to have a silly sounding term, unless you think the silly sounding term is really that important to everything. He talks about the wave function and measurement. This is very important. This is the whole reason why quantum mechanics is weird, right? You have a wave function. You talked a little bit earlier about probability waves, but that's hard to interpret. On top of that, the measurement problem uses the same wave function, which is actually deterministic, and turns it into something probabilistic. And that's where some of the weirdness comes, and why you get these strange interpretations of quantum mechanics. And the more you refine them, the stranger they get, because it's all in your head. Then he actually does go for the Einstein-Podolsky-Rosen theorem, or EPRB experiments, when they put them all together. That includes Bell's theorem. And what Bell's theorem basically showed is that if you look at this paradox that I think it was Podolsky was the real person who did it, but Einstein and Rosen were doing a lot of work at the same time, I believe. When you look at this paradox that they were using to show there was something wrong with quantum mechanics, you can actually turn that into an experiment. And when you do that experiment, you can see if probability is working, either A, normal wave, you expect probability to work, or B, the way quantum mechanics tells you it should work. And you get, if you're very careful in putting the experiment together, different results. If you have something that's acting like classical probability, or you have something that's acting like quantum mechanics. And it turns out, if you do all of this, everything works like quantum mechanics. They did a great, huge study over in Geneva just a couple of years ago to try to get rid of any possible way that you could get around it. I'm not sure if they got rid of any possible way, but it looked like a whole lot. Actually, even before that, it looked like they were probably very close. But there's no possible way to get away from entanglement and just the quantum mechanics being what quantum mechanics says it is, not what you want it to be, right? Based on your experience, not experiment, in the classical world. And then a little bit about quantum interpretations and stuff like that. And we've done episodes in Physics Frontiers about several of those things. On the old podcast, we did episodes on quantum interpretations, period, when we were talking about Aronov's book. But that's more or less what we did. Then he has appendices, and that includes the scary math and references, but that's the scary math right there. So no math for 6 chapters, and then an appendix with scary math for a few pages. Not really enough to teach you anything about it, but enough to convince you, hopefully, that at least the math part is real. The experiment part is real, the math part is real, it's all happy, they go together. What doesn't work is your classical intuition. And so then we go to part 2, misconceptions about particles in space-time. This is the MiniBlack Holes one by John Terning. He talks about particles first. I think he talks more than just about atoms. I think he talks about elementary particles as well, and you build up atoms from those elementary particles. Right? That's our view. MiniBlack Holes talks about why you shouldn't be so scared about MiniBlack holes showing up out of nowhere. Sorry about that. That was scary. I have to remember to move my mouse around more often. Particle colliders in the universe. Why are we not all going to die? And there's a lot of this. Actually, probably that was the MiniBlack holes. But parallel universes and stuff like that. So we do have to keep in mind that a lot of this book is clearing up misconceptions. The previous part seemed to be very much focused on one thing, on quantum mechanics, right? This middle part, misconceptions about particles in space-time, seems more to be about a list of different misconceptions about particles, about these mini black holes, which were probably more of a thing early on when the LHC was first coming out, when the Large Hadron Collider was first going online. People were, for some reason, scared that the world was going to end, as they always are. Particle colliders, physics in the news, and this is cell phone radiation, cold fusion. I mean, they're just topics, right? So this second part is mostly just topics. And then 12 is extras. That's mostly math. Right? This is basically what ended up in the appendix over here. So this makes me unhappy, right? I would prefer this chapter 12 to be more appendices, and they can do them 1, 2, 3, or they could do them whatever. It just feels off, right? It just feels off. This is something I think an editor should have taken care of to make everything seem to be the same, right? Uniformity is good. And then we had Misconceptions about the Multiverse by Nomura, right? And this is talking about the theory of the multiverse. Okay, so I do think that we need to look a little bit at Nomura's stuff itself, and I think that mostly because I don't think it's as strong as the rest of the book. I do think that it introduced some very interesting things that I hadn't known about, but basically, some of the equivalences I think don't really hold up. Right, so he's talking about the basic picture. What is this multiverse? First, here we've got this expanding universe, right? And he's saying that's not the finite universe expanding in ambient space. Actually, we'll have to talk about this in a second. Instead, it's expanding in a finite region. It's a weird idea, but you see, as it's expanding, so are your meter sticks, right? Your meter sticks are expanding as the universe expands. This isn't very controversial. Talks a little bit about things. Calls this a Penrose diagram. I showed you some things when I'm trying to talk about Penrose diagrams. I think it's close enough. At least close enough for me. But he wants to say here, right, misconception, that the multiverse is well-founded. So he says, the misconception is that the multiverse is a random guess, which is not scientifically motivated. So, I don't think most people think that. So, there are different kinds of multiverses, and they come from different places. He's going to care about the one that comes from string theory. That is not the strongest, but it's not the weakest idea. And he's going to mix the one that comes from string theory with the one that feels most likely, right, for there to be many worlds, many universes. And he's going to talk about this in terms of the anthropic principle. So the anthropic principle says that, for us to make an observation, the world has to be such that we have to exist. Not the strangest idea. It's weird that actually gets you anything as far as something working. And actually, Stephen Weinberg, he did that. And it was probably the most famous use of the anthropic principle. And it was just this thing. So here we have our rho lambda, the cosmological constant. Usually it's just lambda. Now it's rho lambda, which is saying it's sort of an energy density. And it says that any of these black spots were, in string theory, for example, the cosmological constant could exist. It won't be, because only if the cosmological constant is very small will we actually exist. Reasonable? Yeah, so the cosmological constant was small. In fact, he said it was going to be just about as large as it possibly could be. I'm not exactly sure what happened with all those dogs and cats. So very interesting. And he's talking about compactified dimensions and stuff like that, which is what's going to give us the multiverse in itself. But then he draws this for us, showing us all the different multiverses in the universe, right? Or a possible schema of these bubble universes. And you saw some of those bubble universes on the cover because this is a new book and that contact paper hasn't smoothed out completely yet. It will. I used to spend a lot of time being very careful about that, but turns out after 2 or 3 years they're all gone anyway, especially if you leave them in the Houston heat. So here's us, and you know, we're in that spot. So now this gets a little bit weird because he just told us, where is it, that this was our model, right? Here's our model. Got a universe that's expanding, but not in ambient space. There's no ambient space around. But this model at least suggests an ambient something, right? And that's a little bit weird. So I'm not sure how to interpret that, because it gets a little more concrete right here. Again, we have that same idea, and it looks like there's something that these bubble universes, including our own, are inside of. So he's put together a couple of different things. Now so far he's just said, well, if there are these universes, they're just scattered all over the place, except there's no place for them to be scattered in. Strange, but you have to think that no matter what kind of multiverse. Because the space is all inside of each universe, right? So if you say there are multiple universes, there's only space in those universes. There's no ambient space outside of them. So you have to think that, and that's okay. That's good. I mean, we think that there's a common origin to space-time somewhere, and that, at least for a string theorist, would be in the string theory somewhere. And here, when he's demystifying the multiverse, he's saying that the multiverse is not mystical, it's scientific and conservative. It's not conservative, but it might be scientific. And this is his analogy, right? And that's very interesting with that analogy. So he's saying here, take special relativity and gravity, you get general relativity most likely, Einstein equation, and that's general relativity. And you get the expanding universe and black holes. You get something out of unification. So this is a unification scheme here. Special relativity and gravity, right, gives us, after unification, things we didn't think about before. Okay, there's a little bit of a problem with that, but we won't get into it. It would allow for, in a way, the expanding universe, but that's all. You have special relativity plus spin, gives you the Dirac equation, that gives you the antiparticle, and you could go all the way back. The classic one is electricity plus magnetism, gives you Maxwell's equations, which give you electromagnetic waves and light, right? That's another one of these things. So there are a lot of ways you can put these things together, right? A good unification, which is one of the things we like in physics, will give you something new. And here what he's saying is that when you take quantum mechanics and you take general relativity and put them together, you get string theory. That's not necessarily true, but it's one way we can put them together. Then you get the multiverse. That's also not necessarily true. So it's also not necessarily true that you can put general relativity and quantum mechanics together. Definitely string theory hasn't been successful at that. But it's one of the best unification schemes out there. It's very good. It's not as successful as he's making it sound. So this is good. It's even better. You know, he does even better than that because he makes a specific prediction. He's saying that because of this sort of exfoliation, because you're getting all of these different universes coming out, and this is actually something that he did, so it's very important to look at, to read him about this. This is something that if Randy isn't completely upset about the multiverse stuff, I'll do it. So, like last time, I wanted to talk about universal constants. Well, not last time, but a couple of episodes ago. I want to talk about universal constants. And there was some multiversality stuff in that, right? And Randy just focused on that, and we got a little bit off track from where I wanted to go. I might have to do a WEP episode about that at some point. I've got one, let's see how time comes together. But it's important that Nomura has probably, he says he has, found a trace or found a way to disprove string theory, or not string theory, but the multiverse. And he says it has to do with space with a negative curvature. Now, it's supposed to be a small negative curvature. We'll find out about that later on. Somebody will figure out a way to observe it. But that's what's going on. So I don't think that's as strong as the rest of the book, right? But I think it's a very good book, and I think it bears looking at, especially if you're a little bit knee-jerk in some of your responses to things, like I am. So we've got Quantum Physics, MiniBlack Holes in the Multiverse by Nomura, Poirier, and Terning. Very good book from this Multiversal Journeys series that is a Springer imprint. Like it a lot, and so I recommend it if you're into something like that. I guess we do have here the bad part about having this not on my phone anymore, which is that I've talked for 30 minutes about one book. Okay. And I don't have any limit on how much space I have on my computer versus my phone. Probably there are going to be some audio issues as well. I'll have to figure those out before I start using this camera for work. I just installed it today. So thank you very much for listening. I'll pull something else out next week. Bye now.